Good evening, everyone. Am I audible?
Yes, ma'am.
Okay, thank you. So, yes, welcome to this week 5 session. Um, so, before we start discussing this, Anupam, you said 50 marks. What problem did you have in the last week assignment? Is this 50 like percentage or absolute score that you are saying?
We have 10 questions. Out of that, 5 question is correct. 5 is not correct. See, now
Mm-hmm.
50 means 5 questions are correct, 5 is not correct.
Okay. So, do you have some specific doubts in any of the question? Also, I think last week they shared the solutions of assignment 1, 2, and 3. So that was what you were looking for in the last session, right?
Yes, ma'am. 1 to 3
Okay,
we got.
nice, nice. Okay. So Shivang is also here. So how was your assignment, Shivang?
Ma'am,
Did
it
it go
was
well?
fine. I got 90% marks.
Okay.
Yeah.
Okay, that is nice. So any question from the last assignment that both of you would want me to like go over once briefly so that we just clarify that doubt right now itself?
Can you show the last assignment, because then we have to log out and then log in.
Yes, here it is. Were you able to get this one right? This was from the paper that I had shared.
Yes, ma'am. This is okay.
Okay.
Yeah, yeah.
How about this?
This ma'am, the answer I got wrong, because I said it is displacement, acceleration, and speed of mass. However, there are only two
Yeah,
what say energy stored.
right. We had
So
discussed,
these
right?
two
That is
variables are there. One is
Mhm.
displacement, one is what you say
Speed.
acceleration. Yes, yes.
No, no,
So
not
this,
acceleration, speed.
sorry, speed.
Right.
So this I marked wrong, but I understood after that.
Okay. That is good at least. Okay. What about this?
This also one is wrong. So I that also is okay. I can now point out what is the error. Next one.
Okay.
This is also okay. This is also.
Hmm.
This is also okay, ma'am.
All right. Hmm.
Next. This is also okay. Yes. Next. So hey, in this, ma'am,
Mm-hmm.
I could not calculate. The answer is 150. I said 151, so it was 115, I think. So this was wrong.
So this was 4 by A and your A is equal to tau into Wn. I mean omega
I
n,
guess,
right?
ma'am, this answer I got 16.
Oh, if both of you got different answers. Okay, let me check. What is the answer that NPTEL says? Give me 1 second, I'll just check it. Week 4 quiz. Second last. 16. You got 16, right? And how much did you get, Anupam? 151.
161.
160. Okay, I think there could be some calculation mistake. Let me check. So this tau value you actually take from here, right? So what was the correct option in this question? Number 5. It was C, right? So let's see, under root k by m.
Ma'am, I
What
think
is
it will be better if you easily just do it by comparing the below thing. You don't have to calculate two things. S square plus 2 eta omega plus omega square. So 2 eta omega is equal to that thing that we calculated there from the equation only that you
this one you
uh,
are saying?
yeah. So I use the equation and I just calculated from there only.
Okay. You mean this entire part directly?
Yeah.
Okay,
Yeah.
okay, okay. So yeah, if we have b
So
by
that will
2
be
under
just B
root
by
2m.
M. We don't have to calculate the two things. That
Ah,
will be
right, right,
directly
over
B by
here.
M.
Yes,
Yeah.
correct.
So that will
You're
make your
right.
calculation a lot easier.
No, but it won't be b by m. It should be b by 2m,
B
right?
by
Because
2M.
we are
Yeah.
taking
Yeah.
2. Yeah.
Yeah. B by 2M. B
So
by 2M.
it should be b by 2m, and is your b is this 2 into
2.
2, but it is 4 into, okay,
1
4
by
by
4
a.
into 4. Yeah.
So
So
it
it
will
will be
be 4
16.
into 4, 16. Yeah. I think there might be some minor calculation mistake, Anupam, I guess, from your
So,
end.
ma'am, tell me one thing. Now,
Mm-hmm.
mass is in kg. So,
Yes.
what I converted into Newton. So that is why my answer is 10 times more. So
Oh, you don't have to. All these are in SI units only, right?
I did that wrong. I multiplied
Oh.
2 into 9.8.
Oh,
So
no,
I
no, you didn't have to do that. Okay, I understand. Maybe you made it like mass into acceleration, you did. Like force. But over here also it is 1 Newton per meter, right? Not 1 Newton.
I converted kg into Newton, ma'am. 1 kg is equal to 9.8 Newton.
Okay, okay. That was not required because over here also in this equation, we directly use what is there.
Next question, ma'am. It is just error of.
Okay, okay, sure. This is fine.
Ma'am, this I could not solve.
Okay. Shivang, you were able to solve?
Yeah, ma'am. I was able to solve.
Okay,
Just by
then
the
help me
hint that
now.
you given that I have to take the input, the state transition matrix for 1 by M comma 0.
Hmm. Okay, so A is coming from our first, like this question number 2, right? So, and you were able to get that right. So for question number 2, oh, you were not able to get this right, and then that question got wrong. Okay, fine. So either A or B is the correct answer over here. So if we take 0, 1 minus k by m minus p by m, 0, 1 minus k by m b by m, right? And this is your B, I guess. Okay, so what does this question want? This says find out h of a, and h of a is given using this. So you need to actually calculate this. First of all, we'll simplify this. It is 0, 1. What is minus k by m? 1 by 1, 1. And b is also 1. So we got this, right? Then we'll have
Okay, minus
0.
1. Yes.
Uh-huh. What?
Yes. Okay, ma'am. Okay.
Okay, okay. So now we have 0 minus 1, 1, 1 minus lambda I. So it will actually be the whole square because both of them are the same matrix. But still, let's see. And then minus 1 and then 1 plus. So you multiply this with the same one and then you will get your answer. So this is 0.864 minus 1. 0.64 minus 1 is 0.36, right? And then 0.8 plus 1.8, 2.6. Oops. Is B gonna come here?
Ma'am, there is a minor mistake I think you have committed. The A
Hmm?
matrix should be minus B by M minus K by M 1 comma 0, I think. Because for 1 by M comma 0, that is the correct answer, no? That's why we have specified the 1 by M comma 0 as an input.
Oh, for one. Okay, okay, right, right, right.
Yeah,
So
yeah.
we
So
had to choose the
that's
second
that's
option.
the error that most of my classmate committed.
Hmm. Right. So we had to choose the option corresponding to this.
Yeah, yeah,
So
yeah.
basically, the
That's why it
option
is
A.
specified. Yeah.
Hmm, 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 hmm. This is 0.04, and then this is minus 1. So it is minus 0.96.
Yeah, the
So
B
yeah,
option.
I mean, there is only one with this option.
Yeah.
Okay, how was this question for you?
This is okay, ma'am.
Okay. Okay, so it's good at least that you understand where things went wrong and you can fix that in the final exam also. So that should be good. Okay, so let's move on to this week 5. So over here, we actually have this delay aware design and platform effect of stability or performance. So let me see if I can go through some of the examples over here. So in this lecture, basically there were a lot of examples and a lot of theoretical analysis. I would like to skip that for this session because you can anyways go back and watch the lectures. It is there. I'll try to go through some of them, which is helpful again in your assignment, and some of them which are in general very interesting and will help you. Maybe final exam questions might come from there. I'm not sure, but those are like hot topics. So I'll go through those also. Okay, so yeah, so one thing is about this sample and hold circuit. So what happens is over here, let's say you have some kind of a where do I start? Let's say you have this analog signal, okay, and then that analog signal is like held for some time, okay, and then it becomes this continuous time system. Then it goes to a sampler which takes this analog to digital. So what is actually happening is, let's say over here, yeah, this example is shown. Let's say this was your initial input. Okay, now when you want to use your sampling, so these are like, let's say this is the interval of sampling. So you want to sample over here, and over here, let's say. Okay, so what happens is at the time you want to sample something, your system will just continue to have that value only. Okay, so this entire part until you extracted the next sample, for you the data point is the earlier sample, right? So in that case the values remain constant for the, like, until you get the next sample from your input signal. Okay, so that is what is going on over here. So this is called a zero order hold sampling, and this is a piecewise constant function. So over here this says that u of t, so this is u and this is x, all right, and this is x t of k, which is, this is continuous input, this is sampling with this at tk time step, and then ut is your output. So this is actually u of tk between tk and tk plus 1. So between this tk and tk plus 1, whatever was your value it just retains until then. Okay, so this was the concept of sampling. Now, yeah, so this is, let's say, d phi by dt is equal to a phi. So how do you represent phi? Phi is represented in like this. Again, very simple thing. And phi of 0 is equal to identity matrix. So E of 80 is given as this. Can you tell me which formula is this?
Taylor series.
Yes. So this is your Taylor series. All right. So now, actually, given these kind of equations, right, we would have these for any kind of model, and you want to like get the state space model out of it. So for any of these ODE, this we have learned in our 11th, 12th class, right, for integration, that you have any formula like this, you first calculate the integrating factor. So over there, we used to call that as integrating factor or integration factor. And now we call this as multiplication factor, which is the same thing. Okay, so that is calculated using this formula for any differential equation of this type. Okay, so similarly, what we do is over here we try to substitute. So this equation and this equation, we try to substitute, and then over here we try to find out a solution for that particular equation. Okay, I won't go in details, but I'll just cover that part. Now, the value of this UT, it changes only at every sampling period. Okay, so UT is equal to this for like t between this and this, like one and the next sample. All right, so therefore this is what is the thing. Now let's see what is important. Yeah, again, this is a very simple notation that your h is actually the sampling period, which is supposed to be constant for any control system. And again over here, so these are the things that may be used in the assignment question, but I'll come back to it whenever they are being used. Okay, so they say that phi is equal to this e to the power ah, that's how you denote phi. And then you have this t, which is b into h, and it is calculated from this part, and this is how you are getting it from. Okay, so now when you have different kinds of system, how did you analyze the stability of the system in the previous session using poles? Do you remember? We had poles and zeros. So can you tell me what was a stable system, marginally stable and unstable?
If poles are at left hand side, then it is
Mm-hmm.
stable. Then it is
What
stable.
do you mean by left hand side? Which means that real part is negative, right?
Yes, ma'am. Yes.
Okay, nice. And next?
If real part is zero, and
Mm-hmm.
then it is oscillating. And if it that j the, the roots are on the imaginary plane, then it is oscillating.
Yes, right. That is marginally stable. So if your real part is zero, your roots will be on the like here and here, something like that. Okay, and how about the unstable system?
If it is the real part is in right side.
Okay, so real part is greater than zero. All right. Now over here, what do they say is for discrete time system stability. Again, it's the same thing about the poles. They have to be less than one. So if you want to like, let's say the radius of this circle is one, which is represented like this. So the absolute values of all the poles should be less than this. Marginally stable, one or multiple poles are one, and unstable is like one or more are greater than one. Okay, so over here there is one question on this actually. Basically what you do is you try to multiply both of them. Okay, and then you see like if it is coming greater or if it is coming less. So over here, if all of them are less than one, the product of all your poles is going to be less than one, right? So that's how you find out the stability over here. Now in this case it can be one or less than one. I mean over here I don't think the multiplication will work. Um, yeah, maybe just for this one it might work because that is probably used in the assignment. Let's see. Yeah, this controllability and observability. So in this controllability, so we say that a system is considered to be controllable if for any initial state x of 0, a control input ut can be designed such that within a finite time t, the state of the system reaches any final state x of t. Okay, so basically you want to say that, let's say this is your initial state x of 0 and this is your input u of t. Now as your t reaches infinity, not infinity, basically it reaches some time, it becomes like as your time passes by, this reaches a final state. Okay, so over here you have to make sure that your t is actually not equal to infinity because you are saying that this is a finite time, right? So this is, if this is happening, we can say that our system is controllable. Okay, so that is actually represented by this. So the, if the above system of equations has a solution if this particular matrix has a full row rank. Okay, so this is actually called as the controllability matrix. So this is how we calculate if it is controllable or not. Okay, so you know what is pi and what is tau. You actually saw over here, right? So given any system, you just try to get this matrix, see if it is a full row rank. If it is yes, then it is controllable, otherwise no. Okay. Now in the case of observability, what we do is we have the system and that is considered to be observable if for any final output yt over a finite time interval between this, it is enough to reconstruct its initial state. Okay, so what do you mean? So this means that it is observable. So given any time, let's say t is equal to 10, even at t is equal to 10, you are able to construct what the output was at t is equal to 3 or t is equal to 1, something like that, right? So you can just get your initial state out of it. So again, for the same thing, you just construct this particular matrix and then you check if it is a full column rank or not. If you have, then your system is observable. All right. Mm, yeah, and some of these formulas are actually used like directly in the um, assignment. One is this actually, it's directly there. Yes, let's check this. Um, so here these are mostly like these three different tasks are there: sensor task, controller task, and an actuation task. And the concept of dependency among the tasks. So over here, we say that these are different sensors. We have two controller and we have two actuators, right? So two sensor input is going to this first controller and the second sensor and the third ones is going to the second controller, right? And based on these two sensors, it is trying to actuate. So over here, a task dependency is shown, which means that you are not going to generate a control task 1 unless you have TM1 and TM2, right? And then your TA1 will not be generated unless you have TC1. But your TM2 and TM3 are, I mean, again, so TM3 does not depend on TM1 and TC2 does not depend on TC1. So this entire loop is independent and the left one is totally independent. But if you go down, the dependency arises. Okay, so that's how it is represented over here also. So if you have TM1 and TM2, you can have your TC1, but at the same time you can have your TM3 also, and then TA1 will be there and then TC2 or is TA2, right? So this is how it can happen. This is one kind of schedule. The other that is also possible is, let's say, TM1, TM2, TC1, TM3, TC2, TA1 and TA2. This is also a feasible schedule. Okay, so this is how it works. But if you want to like say that this is how it is going to work, then you can assign that also. So if you are reading these two sensors and then you are calculating something out of it, then you are reading the third sensor, and then you are actuating it. But over here again, as I said, right, it's not depending on anything from your U1. So this, even if this TC2 comes over here, it doesn't make a difference. Okay, and then you have this actuation and then it goes back to the same stuff. All right, and again over here, so if you see, these are the different times of your implementation. One is called as the sensor to actuator delay. One is called periodicity of the control task. Okay, so sensor to actuation delay is from the time you sensed to the time you actuated. So your TA1 ends over here, right? But it said periodic of task 1, and H1 is this. Why would that be the case? Maybe because that's like the period by when you are supposed to start your task or not. Okay, but yeah, so the ideal design assumes tau1 is equal to tau2 is equal to 0. So this and this should be equal to 0, which means that your sensor to actuation is real time. Okay, or tau1 should be less than h1 and tau2 should be less than h2. So that is over here. Now again over here there is something called as a concept of task triggering. So have any of you heard about this event triggered designs or something like that, or event triggered mechanisms?
Yes, ma'am. In the industrial engineering, like
Mm-hmm.
say, uh, I will give you example. Suppose temperature reaches certain degrees, so then
Right.
actuator will okay switch off that valve like that. So
Mm-hmm.
once that temperature is reached, then that will trigger the another mechanism.
Correct. Yes, that's what is event triggered. So now over here, what we say is that TM and TA, they consume negligible computational time and they are time triggered, right? So TM is like sensing and actuation, but the major thing is this TC. Okay, so this TC needs finite computation time, which is basically your computing, and is event triggered and preemptive. So this is time triggered because you can say that I want sensor data at this time point, or basically your samples, right? But unless you have your sensor data, you cannot start a compute task. So that's why this is saying that this is event triggered, because this is going to start only when this comes in, right? And when multiple tasks are running on a processor, you can be preempted by a higher priority task. That's what we have studied earlier, that if you have different IDs of tasks, the one that has a lower ID gets the higher priority, and that is just for the CAN bus, but there can be different kinds of priorities for different things. Okay, so there can be some with constant delays. You can like go through it, but we'll come back if there is any question related to this. Mm, okay, signals defined. Yeah, I think we can go through this one. So let's say this is your x of t, like this, the wave, and these are your sampling periods. Okay, so at this point, when your wave was at this, so you are retaining this value. Okay, now again you sampled over here, the value reduced, and then you sampled over here. All right. So now, based on this, you have a TK, you have a TRK, and then you have a TK plus 1. All right, something like this. So this is your deadline of the task, computation task, I think. That's what is DC, right? DC is supposed to be, I guess. Okay, sensor to actuator delay. All right. So your deadline is equal to the sensor to actuator delay. Okay, so this is your actuation time and this is your sensing time. And then in between you have your computations, and then you wait for some time before you actuate your uh, whatever your actuator is. And then at the next time you get your sample and then you do all this. Okay, so this keeps on going. And in the case of zero hold operation, again, it's the same thing that we studied in the first two slides. If you like whatever is there for the previous step, and then this is for the next step. Okay, so that's how we put it over here. This just shows that what is happening within one sampling period. Okay, like you have sensing, you have different computes, you have an actuation, and then there may be some waiting depending on how heavy your compute is and what kind of device you are using. Okay, so these are fine derivation. We can skip. What all is there? Yeah, this is probably required. So let's see. So this augmented system model where you have the delay less than your sampling period. Okay, so in this case, what you do is your x of k plus 1, that is equal to phi of xk, plus this is your tau, and then plus this is your tau naught. And then you have y is equal to this. But when you want to augment that particular system, you say that your z of k is equal to x of k and u of k minus 1 transpose. So that comes from here. So with these new definitions, you just change the state space, and then that's how you redefine the variables. Hmm. And I think there is one question specific to this particular slide. Um, because over there, the question is asking what is the feed forward gain or something like that. Okay. So we'll come back to this because we anyways have to go through it. Yeah. And then again over here, let's say you have a time continuous time system, and this is your state space. So you have x dot is equal to a of x plus b of u, right? And y is equal to c of x. So this is your a, this is your b, and this is your c, right? So you have to compute the system model considering ZOH with sampling period this and a constant sensor to delay this. Okay, so you have this formula given to you. So eventually you calculate these things. All right. Um, yeah, that's your system model. And then augmented states is calculated. I think we should just keep it for now. These are all examples. Okay, let's go back to the question. So any doubts up till here? Like something that you want me to discuss specifically before we start discussing the assignment? Okay, if there is nothing, let's go to this. Okay, so this is another question. So last time we had buck converter, right? DC to DC. Yeah. So similar to this, what we have to do is we have to take one variable as the current in the inductor and the second variable as your voltage on the capacitor, as these two are your energy storage elements. All right. So depending on this, let's see what we can do. So there is this very nice article. So I would suggest you to go through it and maybe save it. So over here, probably if you go specifically to this question number, example 3 on page 9. So that's a slightly, changed circuit. You have a resistor, you have a capacitor first, and then you have the inductance in the PDF that I just shared. Are you all able to open that link?
Yeah.
Okay, nice. So if you are there, so there is one thing that they are also calculating, which is your V of C, and that is capacitor voltage. And then this is your I of L, that is your inductor current. Okay, so you can just generate the state space equation using that. Yeah, I think you should get some value of A, B, and C, and D will be 0. I don't think there is any D available, right? Consider this circuit where U is the input to the system and Y is the output voltage. Can you express the system in the form of a continuous thing? Yeah, I think. Yes, you should be able to calculate this. Okay, so should I move on to the next question?
Hello.
Yes. You have a doubt, Anupam?
No, ma'am. I thought that something is wrong.
Oh, okay, okay. No, I was waiting in case this example is fine, or should I like move on to the next question? Let me just check one thing. Continuous time, state space. So that is given by Okay, so the next question says that discretize the above system for a sampling period of 100 milliseconds, and which of the following represent the state space of the series RLC circuit system. Okay, so it is for the same question, but we have to like discretize it now. So what do you have? You have x dot is equal to ax plus bu, right? And what was the equation of your phi? It is actually from here only. So this part. Okay, so this is your e of at. So your phi is given as e of at, which is nothing but I plus at plus a square t square by 2 factorial, and it continues, right? And then your this is b by a e to the power h minus 1, right? So now if you want to, what is your sampling period? It is 100 millisecond, but in terms of second it is given as 1.0.1 second, right? So you will calculate your tau first. Okay, e to the power 0.1 into a minus 1. Hmm, yeah, so I think if you just go through these slide 5 to 8, sorry, 8 to 11 exactly, that's where it will solve this for you. Okay, this week's assignment is a bit tough, and you would need to refer the lecture again and again because it's more like mathematics and all those equations are involved. Okay, so you would have to like go through each step over here. So in the case of this x dot, you need to get this multiplication factor first, and where will you get this from? You get this from the question number 1's answer. This is slide number 8, 9, 10, and 11. Okay, so that's how you discretize your question. So you have to put it in this format.
And tau we can take approximately b into h
B into
matrix.
H, yes, you can do that. So I think whatever B you got from here, you can just multiply that by H and you can get the answer. Is this okay?
Yes.
Okay. So let's go to the next one. It says given a final state of the above series RLC circuit system after t units of time. So after t units, you got to a final state. Okay, so is it possible to conclude a unique initial state for a sequence of input signals? So what does this definition talk to you about? It talks about the controllability, right? Because over here we say that at you have x is equal to 0 at some t is equal to 0, right? But after a certain point in time, you reach your final state. Like this is your final state. And this time is actually a finite time, right? So over here the question is the same. You have a final state after t units of time, and this t is your feasible, I mean finite time. So is this possible to conclude this? So if the question says, is it possible to conclude a unique initial state, which means that the equation should have a unique solution. And what do you mean by unique solution? It means that your that matrix that is there, controllability matrix, that should be BAB, that should be like the rank of row should be like a full rank, right? So you would need to calculate in that basis. So you get the b from the above equation, like this one over here, okay, and you get the a from top, like that you had, and then you multiply that. So the first one will remain as it is, the second one will become a, again 2 cross 1 vector, and then you have both of them, and then you calculate if what is the rank of that particular matrix. Okay.
I mean, this we have to take first wala ki that discrete wala.
Take question 2. hmm. I would say take question 2. Or maybe try with both if you are very doubtful. Okay.
No, because the time t is continuous, so it is not
Mm-hmm.
tk plus 1 or tk plus n. So I think one will be okay.
No, but it says t units of time, right? There is the concept of units.
Okay, we will try with both.
Huh. Prioritize question, I mean, whatever you get from question 2, and then check with question 1 also. But very likely you should be able to get your answer with question 2. Okay. So again, the same thing. You have to get the observability matrix for the series RLC circuit in question 2, where the second state is considered to be the output of the system. So, okay. So here you have to get this C and CA. You have to get the transpose of that. Okay, and if you think that is okay, no, this is just the matrix. So you just calculate the matrix of this. This is your observability matrix. So C from your above equation, question number C will come from your question number 1 because it did not change in the question number 2, right? When we were changing it. So over here, I think C and D don't change. It's just that your A and B only change. But just confirm once, like when you solve it. Okay. So your C and D will come from question 1 directly. And this A comes from your question 2. Okay. So let's see this. Consider the following trajectory tracking control, okay, system for a vehicle of mass m that tries to minimize its deviation x from a certain reference distance by exerting certain input force u to overcome the equal amount of force inflicted due to friction between these two. But due to the wind drag and rolling resistance, the vehicle faces a backward resistive force Bv, while the vehicle moves forward in v velocity due to the force applied. Obviously, the equations are simplified and complexity that arises due to power drain is omitted. So you have been given a mass and a b, so you have to find out whether your system is stable in open loop or not. Have you seen this equation somewhere? We solved this in the last lecture, right? Let's see where this is. It was a similar one. Okay, I don't think the car one is here. It was probably in the week 4 lectures. Let's just check once. Hmm. This is the same question, right? So what is the slide number 9? Okay. So what happens over here is the same thing. So you have BV, which is the friction force. Your mass is m, and then you're going in this at a speed of u. So, and it's the exact same thing, right? So now that given you have this equations, let's see. So your equation is this: mv dot plus bv is equal to u. You have mv dot plus bv is equal to u. What is the other one? Your y is equal to v, right? So now you have to just check if your system is stable in the open loop. So by stability, what will you have to do? You will have to go through this Ackermann's formula, right? Or maybe let's just see. So if this is your mv dot, which is basically mx double dot plus bx dot, that is equal to your u, right? And given this equation, so last time you already solved it. It is probably here somewhere. Should be in your notes. Okay, so what do you have over here? Your x1 dot and x2 dot, that is equal to 0, 1, 0 and minus b by m. You have x1, x2 plus 0, 1 by m of u. Okay, and then your y is equal to 1, 0 of again x1, x2 plus 0 of u, right? So this is how we got. And over here, what do we say? My x1 is equal to x and my x2 is equal to v. Okay, so if this is your equation, you can try and get a, the eigenvalues for your equation. So get the eigenvalues of a and try to see what is the value of those roots. Okay, and then once you have that, try to do this analysis, the circle analysis that we had. Where was that? It was somewhere here only. Yeah, this one. Okay, so then you do this discrete time system analysis and you should be able to get the answer. Mm-mm. Okay, so I'm putting it over here. Is this okay?
This is analog system. If we take A, what you've decided.
Mm-hmm.
So A we can calculate whether this is stable or not.
Yeah. So if you just, yeah, if you
So
have
now
that
if we,
matrix. Mhm.
yes, if we say A is 0, 1, 0.5, minus 0.5. So we have to calculate this eigenvalues. If they are less,
Correct.
then it's stable.
Yes. So once you get your eigenvalues, right? Okay, then you like get the max of lambda 1 and lambda 2, and if that is greater than 0, basically if this is greater than 0, then this is going to be unstable. All right.
Yes.
Okay. Okay, so let's go to this question. It says design a controller for the same, given in question 5, such that the closed loop discrete system poles are placed at 0.2. Okay, so right now your poles are at 0.2. If the sampling period of the controller is 0.5, find the correct answer from the following points. So what do we have to find?
To find K,
Okay,
K,
we have to find K. Okay, no problem. Let's see how we can go about it. So if you have this x dot is equal to v, right? And then we have our v is equal to what? V dot is equal to, like from there you would get something like your m into x double dot plus b into x dot plus is equal to u. So you would get minus 0.5 into v plus 1 by 100 into u. Okay. So if you want to write that in this format, what do we get? It is 0, 0, not minus 1, it should be plus 1, minus 0.5 of u and v, x and v. Okay, so your a is actually this and your b is actually this. All right. So now when you want to convert it to this discrete time system, and your time, I mean your sampling period is 0.5 second, right? So you have this if you want to convert, and then your b of t in discrete time, it will be 0 of ts. All these are given in the first few slides of the lecture, so don't worry about noting this down. Okay, so basically once you have your ad, uh, so this is your ats, that is going to be 0, 1, 0 minus 0.5. What is your ts? 0.5, right? So this is going to become 0, 0 minus 0.5 and 0.25, right? Minus. So once you get your ADS, I mean ATS, you need to get the e to the power ats. So what is that going to be? I plus ats plus ats the whole square by 2 factorial and so on, right? So eventually you just take this much portion, right? And then in the end you are gonna get this as your AD, which is 1 0, 0 0.5 and 0 0.75. All right. And your B also you are gonna get approximately this much. I'll just write it down for you, but you should solve it. Okay. So now you got these. So now what do you have to do? You go to this Ackermann's method, okay? And then over there you try to fit in the equation
Ma'am,
these
we have,
values of B and A that you have gotten. Yes?
ma'am, excuse me, ma'am. Hello,
Uh-huh. Yeah, yeah.
ma'am. For linear, what you say, linearization, we have to only take two terms. You have taken three terms in E series. Why?
You can ignore this, no issues. I mean, even if you take it won't matter because it is gonna come very less. Your A is less than zero. I mean,
But
less than
but
one.
we say we do linearization, ma'am. So in linearization, we have to only take two first. This is my doubt.
Hmm. I am not actually sure about that. But in general, we take only these two. You are correct that way. But many a times we also take these three. We don't go to the cubic part. That's for sure. So you
What
can
is the
calculate using these two. Uh-huh.
ma'am, PD matrix is 0 and 0.0025. BD matrix is not readable. Hello,
Yeah, yeah. BD matrix is here.
0.
Zero. Okay, it's not readable. 0.0025, right? And 0.004375. When you use Ackermann's formula, you substitute the pole that you have, this value, you substitute this A and B, and then you try to get the solution from there. Okay. And I think, hmm, give me a second. Mhm. Your mass is 100 kgs and your B is 50 Newton per meter per second, right? Um, Probably you might get something which is this divided by 10. So just check that once, okay? Probably they have this decimal over here. Because when I solved it, I got less. I mean, like not this unit, but divided by 10. That would be one of your answers. Is that okay?
After this AD and BD, what to do, ma'am? What is the next step?
Ackermann's formula. So go through the last lecture, the last slide probably, like around the end of the last. I just pointed. Yeah, there were two steps, right? One was direct substitution and the other one was this Ackermann's formula. So if you already know the roots, like the poles, then you actually go through this equation. Okay, you substitute that and then you try to find out the answer.
This is for what you say analog system. So we have to convert into digital system. This formula.
No, you don't have to do anything. Uh, just a second. So this is your key. which you took all the eigenvalues. No, I don't think you have to convert anything. I'll write the formula for you if you want. So you have to calculate your k, right? And these will be your lambdas for this particular equation. Okay, so get that, and then similarly over here, like you have this inverse, right? So you would have inverse of b comma ba. Okay, and then what do you have? You have h of a, and what is your h of a minus lambda I. So you will have a minus lambda 1I into a minus lambda 2I. Okay, so try and work with this maybe. A minus lambda 1I minus lambda 2I up to a minus lambda ni. Yeah, so you should be able to get something.
The first bracket of K is the lambdas of AD, not AD.
Okay.
First bracket, what you said, ma'am, is the lambdas of matrix AD.
Yes, yes, eigenvalues. That's what is here, right? You just put all of that over here.
Okay, ma'am, we will try it. Next question, ma'am.
All right, okay.
Ma'am, lambda 1 and lambda 2 both will be 0.2, ma'am.
Why 0.2?
These are the poles given. Poles.
No.
For
Actually, give me one
Yes,
second.
yes. HA is the poles,
Oh
ma'am.
yeah, sorry. These are the poles actually, not eigenvalues. I'm sorry. So these will be 0.2. Mm, desired closed loop poles at this one. But is this equal to this? No, these are eigenvalues, right? Just a second. I don't think these are poles. These should be the eigenvalues, but just check
Zero
once.
zero
Okay?
zero one. 001, ma'am. 001.
It won't be 0, 0, 1, right? This is a 2 cross 2 matrix. There will be only two eigenvalues for that particular matrix. Is this okay? Should we move ahead?
Yes.
Okay. So the next question is, if there is a delay of 0.4 seconds between sensing the current position of the vehicle and calculating the required control input to the vehicle to minimize it, what is the new augmented state transition matrix for the delay aware system? So what did we have our AD? 1, 0, 0.5 and 0.75, right? This is what we have from here. So now you want to augment it. So we actually saw one formula for augmented matrix. Let's see. Do you remember where it was? Yeah. So this is DC that we have. Let me just write it down. So your DC is actually 0.4. Okay. So let's see. So you need to calculate this. Your phi aug is equal to phi 0 tau 1 DC 0. This is 0.4. And what is your phi? Your phi is actually your AD. Okay? So that way you calculate. I think you should be able to get the answer. So this portion will be your A. Then you will have 0, 0. And then this will be your tau 1 of DC. And then you will have another 0. Yeah. Yeah. Try to calculate using this. You should be able to get your answer. Okay, the next question is actually a very, very direct question. So if you just go to slide 46, you should be able to get your answer from there. Okay, this is more about the feed forward gain for the closed loop delay aware system with characteristic matrices phi, tau, and c, and with a controller gain k. So one of these was the answer, and I had pointed you to that also. So you can just go and substitute this. Okay, the next question is, which among the below options are correct combination for the discretized series RLC circuit system in question 2? Okay, in question 2, which was the RLC circuit, okay, and the discretized trajectory tracking control system in question 6. Okay. So you will first have to assess what is the stability of your question 2. Then you assess what is the stability of your question 6. Okay. And using both of that, Yeah, using both of that, you can just check like whatever is the option. So open loop system, you just check what was the stability for these two. But just make sure that you have the, sorry, discretized series. Okay, I think one of the answers you already have because we calculated that over here, maybe, yeah, in this part. So you can just get the answer from there. All right. So the last question says, find whether the following statements are true or false. Okay. In absence of the rolling resistance, the trajectory tracking open loop resembles the series RLC circuit system. In absence of this, it resembles the trajectory tracking system. And the past control loop is considered as another state in delay aware system design. Yeah. So this one you can mark as true, that is there because it is coming directly from our theory. But yeah, anyways, all the options have true as the option. Fine. So for these true, try to see that if you remove one of the variables, what happens to your system. Okay, so you just have to tune the parameters. Like if you have, let's say over here, if you have the R, right? So you just put that as 0 and see what happens to your um, system. Like how does A look like for both of them? Okay, A, B, C, like simply all those things. Okay, so I think this is it. But if you want me to discuss anything else, please feel free to do that.
Who is the other student? Ma'am, Shreyash. Hello.
I think Shivang was there earlier.
Get Shivang's number.
Number I won't have.
Hello.
Like, yeah. I actually don't have any students' contact also.
Number because we'll discuss the.
Maybe reach out to him on LinkedIn if possible, because even I don't know. And if he was here, he could have responded at least.
He's available, ma'am. Actually, I don't use any what you say LinkedIn or
Mm,
WhatsApp.
no, he hasn't. Like, he just left the chat, so we don't have access to that also, like his email ID.
Can I get
Sorry?
can I get your email ID?
I don't have access to that. You can either check with NPTEL or reach out to him separately. Um, by the way, don't you have a Google group? Are you a part of that?
No, ma'am. That is what we have not made a group also because at times,
Oh,
okay, professional. I am
I
not.
think you should do that. Let me check that with NPTEL and let me ask them to create a group for all the participants. That should help you, right? Okay.
Yes, yes.
Yeah, because even we don't have access, so how will actually that happen? Okay. Let me follow with NPTEL on this and we can help that way. Books to refer. I would suggest go through the lectures of like whatever is uploaded on NPTEL. Go through the lectures of the week. 90% of your doubts would get cleared over there. And even if not, in the lectures itself, references are mentioned, so you can just go through those references. But just for control systems, I think there is a book. Let me just get it. It's a very famous book. You might even be able to get a PDF for that. Mhm. It is this one called as I.J. Nagarath and M. Gopal. So that's a very famous book, and most of the control systems part is taken from there. So, but since a component of the course is that book, right? I would not suggest you to buy, and you can just get some PDFs for the particular chapters that are over here. So you can. Okay, great. Okay, so I think officially we can close the session. Thank you so much for attending. We can meet next week, 6 p.m. again. But again, if any of you have doubts, please let me know. I'm there until 8 p.m., like till the end of the session. Thank you.